Alright, so here's the weird one. Here's the one that doesn't actually directly show up in our unit circle. I didn't end up talking about this when I first brought up SOHCAHTOA because it's a little bit of a weird concept to understand. So there are technically a couple ways to kind of get the value, but I'm focusing on one of them because ultimately they're all the same. It's just a way of viewing it. So in this case, we're going to start off with our unit circle. So we know that within our unit circle, our maximum value here is 1, 1, -1, and -1 because our radius is set as 1. And that if we take any angle as a degree or a radian, by drawing out that line, the radius is set as 1, and we could determine our sine and cosine values, where sine is set as the y value here, and cosine is set as the x value going across. Now, where does tangent come in? So we should remember that the tangent of an angle is our opposite over adjacent. So of course, yes, you can just take your sine value over your cosine value, and that's how you get your tangent. Though more notably recognized as opposite over adjacent. It actually shows up on our unit circle as a measurable line. So, as we should remember, every line has a perpendicular, can have some perpendicular line to it. So, a tangent is just a perpendicular line to the given angle. So if we drew out a perpendicular line, so here, this line right here touches this circle at one distinct point only. It does not intersect any other part of the circle. It is specifically this one minute piece right there. So now if we were to extend this line, we could see it does two things. One, it eventually hits the y-axis. But more importantly for us, it eventually meets at the x-axis somewhere. In this case, it's not too far off from 1, but as we will come to notice, it can grow very, very large. So this value, starting at that point of intersection, to the point it touches the x-axis, is actually our tangent. That is where we get a measurable line for our tangent so that we can actually see where it comes from. Now, I made mention that this can grow exponentially. And a nice little visual for that is if we just kind of clear up a little bit of our lines. Let's say that that isn't where we decided to set our angle. Let's say our angle was somewhere really, really close to almost 90 degrees. So as we get to there, well, we need to make a perpendicular line. That perpendicular line is very, very close to being parallel to this one. So if it's that close to being parallel, the line that we are extending outwards to is going to slowly, ever so slowly, eventually meet onto the x-axis after we extend it. So, of course, this isn't exactly the straightest line, but if we actually created a directly straight line to it, then we could see that it would go off of the board, and that's where, somewhere off of this board, we will end up meeting it, and you could see that it grows very, very large, very, very fast. So that's why the closer and closer you get to 90 degrees, the larger it gets. And that's also why when we get a perpendicular line to a right angle, then we have two right angles set between the x-axis and that line created, and so they become parallel. A parallel line will never touch that x-axis, and so we cannot actually measure the value it is, and so it technically becomes infinite. So now stepping a little bit away from our unit circle, just enough that we start looking at the actual graph of it. So just like with sine and cosine, we're going to just worry about the increments of our unit circle, going from 0 all the way around to 2 pi for radians. But you may notice that I'm only labeling the x-axis here. The y-axis, since I had just mentioned, it's going to be going infinite. So there's no real point in saying that, oh, well, here's 1 and here's -1, because it's going to blast past that in an instant. So now, if we're going to take a look at our unit circle for just a moment, then we're going to go along the same process we did for cosine and sine. So as we start at our radian of 0, we are going to move up to our first increment of pi over 2. So at this exact point, our perpendicular line is set at, it needs to meet x. So it meets x immediately. There's no distance it needs to travel. It is already at the x value, and so we start off at 0 for our x, for our y. So now as we go upwards, eventually it's a very, very small distance to a slightly larger distance to an even larger distance, and as we kind of saw, it'll eventually kind of grow to the point that it eventually becomes non-existent and you cannot measure it. So we have a slow progression of small changes until it just shoots up. Now, it is very important to recognize that my drawings are not directly to scale because there is a space exactly at pi over 2 that this graph does not touch. It can get really, really close to it. It can get to the 100th decimal of the number before it. So in degrees, you can get to 89.9 100 times. And it won't touch that line, but the second you cross over to 90 degrees, it does not exist. You cannot measure it, as we have kind of seen from the previous image. So at this point then, we then start at pi over radical 2, pi over 2. And as we go to our next increment of just pi, we need to know where we're starting at. Well, if the value that we get here at really, really close to 90 degrees, or pi over 2 radians, is extremely large, we need to mimic that by trying to get to the x-axis. So just as an example, if our perpendicular line is here, in this case, the right side will eventually touch onto the x-axis. Here, the right side goes off into infinity and does not touch our x-axis, so we need to look at the side that actually reaches the x-axis. So at the point here, eventually going forward, we'll meet the x-axis, but it meets it at the negative section of it. So, since it's meeting at a negative, then it continues going negatively. So we're starting off, and again, noting that the value here does not exist. We start off at extremely close to this value until we eventually get to 0. Now you could basically think of it as this way, as looking at it, if we're moving from the right, so at our center point of intersection, let me move this over to here. Say this is our center point of intersection for the line. If from this point we have to move to the right, well, moving to the right is typically seen as positive. So that's why over here, from our point of intersection, we are moving to the right to hit the x-axis. We have a positive slope. If we have to move from the left, that is seen as our negative. So here, our point of intersection, no matter where it is, if we go right, the positive direction, we don't actually get a value for x, value for this length, but if we go left, our negative direction, we do get our value. So that's why we start off in the negative section here. So in this case, eventually as we get to pi, where pi is set at 0 because there is no change immediately at this point, you're at the x-axis already. So that just goes in as a drop such as this till we get to that 0 point. From here, you would have to kind of think of it as upside down. So at our points as we continue going forward, from pi to 3 pi over 2, it is almost like looking at an upside down version of our circle. So if we're upside down, left is right, right is left. Best way to see it is if I take this, actually flip it around, then we are actually looking at our upside down version of it. So in this case, any value, so at any point of our intersection for the line given, in order to reach our x value, we have to move to the right, making it positive, which is why starting from here, we end up with a slope in the positive direction. I'm just going to flip this back over. So that's just to maybe try and help to see that although when we have it right side up, this right here looks as though we're going left, if we're actually viewing it from the 0 point to our -1 value here as up, then this is actually the right direction. So this bottom part of the circle, bottom part of the hemisphere, we want to kind of think as a little bit backwards, where left actually means right and right actually means left. So we'll see that kind of in action again in just a moment, but remember that as it reaches this point here, it has another one of those infinite paths parallel, so it cannot actually reach 3 pi over 2, but it can get extremely close to it. And that's why when we start curving back into our 2 pi from 3 pi over 2, we get that immediate, extremely large number to work with. And again, since this bottom hemisphere needs to be thought of as a little backwards, even though we're moving right, to get to the x-axis, we're considering that as our left, which is why starting at the negative, going up until we hit our 0 once again. And this pattern continues on and on going forward. Hopefully, this kind of helps understand with a little bit of a visual. I left a animated GIF at towards the end of this slide that actually incorporates all of the trigonometric functions between sine, cosine, and tangent. This is hopefully kind of a step-by-step process of why these happen and where we get them from. Um, After this, we're going to be actually changing these tangents, sines, and cosines uh, and using them in different functions and getting values from them. So it's just good to get a understanding of the graphs and where these values actually come from. Why it is that a sine and a cosine can only be between 0 and 1, while a tangent, you may notice, goes up to an infinite number, can be as large as 1,000, but also as small as 0.2. So hopefully this was helpful. I hope you enjoy your day, stay safe and healthy.